and I will kind of give it like, I guess the objective here is to kind of explain not exactly what's going on in the lab manual. I'm going to take it from like another route, and the route that I'm going to take is to explain kind of a simpler system, which is a driven damped harmonic oscillator. And I'm going to tell you where these things come from, because what we used last week, which was that Giancoli textbook, which I thought was pretty good for those, at least getting your feet wet in those differential equations, like here from last week. I think this was really good, but the derivation of these equations wasn't done in the same way, and I had a hard time following it. But what I can understand is a damped harmonic oscillator, and I find that there's a lot more literature on that. I was looking through a lot of other electromagnetism textbooks, and I couldn't really find a satisfactory derivation of this. So I'll just do an analogous system and explain to you, what this equation means and where it comes from, what resonance means and things like that. So one thing to note is that we already kind of know, firstly, I mean, this, we can just ignore this part up here. Basically, it's synonymous. What I will be, well, I mean, frankly, I'm gonna, talk about deriving this, and then we're just gonna apply what we know from this to this. So this is very similar to the equation at the beginning of last lab, where you just get it from Kirchhoff's law. You take things around a loop, and the voltage drop within each of the elements needs to sum to 0. So it's a similar thing here. We have a inductor, where the inductor one was the derivative of I. I is the derivative of Q. And so we have Q double dash, which is the second derivative of Q. The first derivative of Q is I. So this is the V equals IR from the resistor. And this is from the capacitor, the QC that we know from before. If you remember the kind of tau constant that we used last week in the inductor lab, well, this is the same thing, not exactly the same thing. It's actually the inverse of tau. So that what we'll, I'll show from a mechanics point of view, this tau is like the time it takes to decay, and this parameter gamma they have here is called something called the damping constant, or the decay coefficient is another good word for it. And this we also derived last week, or I pointed you to that good derivation here. This was, what we verified in the second part of lab down here. Now I want to kind of jump to what I think is, one of the best classical mechanics books. I used it a lot in college, John Taylor. So I'm going to jump to, let me get my page notes out. So I'm going to talk about a very analogous system, which I kind of have been pointing to all semester, that a lot of these circuits we're working with can be analogously thought of as carts, with springs attached to them, or with friction moving along them. So this is our normal one. This is like the F equals KMT or KMX. This Hooke's law from last semester. We're going to advance this a little bit and look for the solutions of it. At first, the solutions of an equation that looks like, x, the second derivative of x plus omega squared x equals 0. That's, if you take this to the left-hand side. The first things that pop out are exponential functions, because if you take a derivative of an exponential, you just get the thing down from the top, but it just stays the same. But if you do that with something with an I in it, they kind of cancel out, and you get something, that factor of omega, it'll come down. So you have an I omega, and then you do it again, and you have another I omega, and the i's give you that minus sign. Equivalently, another way to write exponentials like this is to write, so here the author just says that in general, a superposition can tell you the most general solution. So instead of taking just one with a plus or a minus, we can take both. What we can do next to simplify this is noticing that this is just kind of an oscillatory thing. Like it's kind of like a cosine or a sine, but it's both of them actually. So what we can do instead is to write it as one or the other. Let's scroll down here a bit. So for instance, let's say this was one of our, like, the plus omega t oscillating like that, and the negative omega t oscillating like that. One thing that we can do, which is called a phase shift, to give you some intuition for it, um, if you were to shift a cosine by 90 degrees, so when I say 90 degrees, you're just moving along this, kind of angle x axis. So if you move the cosine function, or equivalently the sine function, up or over by 90 degrees, or equivalently pi over 2, the functions become the same. So what we can do to kind of take that double, the C1 and the C2 from up here, we can write them as one coefficient with a phase factor. And so that's what this solution here looks like. Now let me skip a little bit. This gets a little bit much. We might come back to that. No. 185. Okay, so here is one. This is in the absence of a force. So if you'll, this is kind of like a cart moving. That's F equals ma. This is what's called like a damping force. So for instance, B could characterize like friction on the thing that the cart is moving on, and then again this kx is for the spring. So what I was pointing at a lot earlier in the semester when we started working with these circuits is that you can draw a completely analogous equation from these circuit formulas. So if you look here, the only thing missing, of course, is that force that we will end up applying, but that'll come in just a second. But these equations for a cart with some damping coefficient and a spring is exactly the same as what we'll use today. So the things that you can take away from this are mass is equivalent to inductance. And the reason for that is that inductance is kind of like its own battery, like it's storing energy. And actually the easiest way to understand why mass is kind of like stored energy is actually like Einstein's E equals mc squared. Like if you have mass, it has the potential to become energy. So that's the easiest way to understand that. And this one's kind of easy. The friction, this thing that characterizes how much friction we have, that's like the resistance. It's how hard it is for the charge to go through the circuit. And this one's quite hard to understand, and frankly, why I struggled so much when we were doing that derivation in the capacitance lab. I like to think of capacitance just as that that coefficient that kind of links up those two derivations that we did. We did Gauss's law, and then we did the potential over the distance. And I like to think of it as just, linking up Gauss's law with a potential theory. And it's the thing that allows you to make those two things equal. But actually, physically, you can think of it as kind of, I guess, the inverse of a spring constant. I'm not exactly sure what that means. I'm sure that Wikipedia article I linked when we were talking about system equivalence, when we first brought this up, could do a better job. But I've been confused since we did that. So next we can kind of begin to take this force in. One thing I'll note, we can ignore this 2. It's just kind of a convention in classical mechanics books like this to have a 2. I don't remember why. I knew last semester, but I forget. But one thing you'll notice is that this beta is like our gamma. So why is that? We already showed that B is kind of like R from this equivalence. And we showed that M is like inductance. So if we look over here, we see that that is exactly what we have over here. If we identified B with R and L with M, our gamma, the damping coefficient or damping constant, they have it here, or you can call it, a decay parameter or something like that. is exactly this parameter minus the 2. And similarly, the thing that we derived last week for the inductance is exactly the same thing as like, that the frequency of the harmonic oscillator, where it's the square root of k over m. Of course, you can square both sides of this. And then remember that we said that k is like the 1 over the capacitance. And again, m is like the inductance. So you can call this the natural frequency. We call it, I think, the resonant frequency for this lab. But those are some of the reasons those derivations link up. Next, let's scroll down to applying a force. So we'll modify that 0 on the right-hand side of the equation above and get an F. So this F is very similar to the voltage that we apply. He calls it like this EMF or voltage like this, but we can just call it a V like we do over here. And one way to simplify this equation is to divide everything by L and then start working with just things in Q's. So over here, I'll kind of put this aside for a moment and look back to the A over here, or equivalently the B over here. Okay, so first thing, either dividing by L, or in this case, we'll divide by M. So if you divide all of these coefficients by M, that ends up giving you that coefficient we had before, the resonant frequency, if you call it. And ignoring this 2, this gives us that damping constant. So here we've divided this equation, everything by m, and we've kind of called this the force over the m, this coefficient like force per unit mass, where over here we do the same thing, force per unit inductance. So the next step is kind of, let me get past this. That's not, I mean, it's formal, but I think it's easier to learn by doing. Kind of like a more formal way to go about differential equations. So here is exactly the kind of force that we're going to apply to our system. It's a sinusoidal. So we're going to apply with our function generator a sinusoidal function. And then if we look over here, there's nothing, this is kind of the trick that we'll pull to make things a lot easier to solve this equation, because we would like to use complex numbers. And the reason for that will be clear in just a second. But if we have a sinusoidal function here, there's no reason that it can't be, there can't be another solution. So for instance, I'll just call it x and y. There's no, both of these equations can totally be true. And in order to switch to complex things, we'll use this formulation of a complex number over here. And the reason we do that is because then we can change things into exponentials. This is something called Euler's formula. It's kind of this relationship between the real axis here and the imaginary axis. And you can kind of relate exponentials to trig functions in that way. And so once we've done that, we assume our function, because if we add this to this equation multiplied by I, we get the following equation. So the whole left-hand side looks identical, but the right-hand side, now we have something that looks a lot easier to work with. Because if we assume the solution is also sinusoidal, which makes sense. I mean, if the function or the driving force up here is sinusoidal, it makes sense that the position or our charge will also be sinusoidal. And so if we assume that, we can assume it in the complex area. And this makes things much easier because if you look at all these z's, all of them will pick up that same factor, which we can just drop out because this is a property of the exponential here that when you take a derivative of it, the thing stays. So like all of these terms will end up having this exponential over here. And so now we have kind of a way to more properly analyze this assumption that we made. So we guessed, this was a guess, it was a guess solution. And we're trying to determine what exactly the form of it is. So this C here is a constant for now. But if we look at this, we have on both of the sides, we have a factor that we could like to be equal. So imagine if we were trying to make this equation into E I omega t equals E I omega t. What would we need to happen? What would need to happen in order for that to be true? Well, we could bring this factor in the parentheses over to the left-hand side. And if C were equal to that, they would both cancel, and we would have, EI omega t equals EI omega t. And so now that we have this, we're going to introduce one more part about complex numbers, which is that you can expand them. Oh, I'm sorry. This is the same part of complex numbers, that you can look at any particular complex number in kind of a plane. So, for instance, you have a real coordinate and an imaginary coordinate, and you can kind of characterize them by phases. So here they use the theta instead of the phi that they're using over here. Or actually over here, they're using a delta. And the way that we can kind of simplify this is to note that if something is real, so because we assumed a complex solution, this is a complex number. And we know that complex numbers can be made from these two things by that Euler's formula I had over here. And so we have a real number, e to the I of another real number. And the way that we isolate this a to solve for like the kind of amplitude of our function over here is to take the complex conjugate. And the complex conjugate is something that if you do it to a generic number here, all you do is you switch the sign of the complex part. So for instance, if a given number was a plus ib or bi, you would just switch the sign to minus ib. So it's kind of a mirrored into the imaginary plane. So a real, this quantity here, its complex conjugate denoted by this star is just flipping the sign of the imaginary part. So imagine that if we do that to this equation, that's one way that we can get A in terms of C. Because if you take the complex conjugate of C, you do the complex conjugate of A and e to the I delta. Well, A is a real number. So imagine that we had just X and X. There's no flipping because there is no imaginary part of A. But there is an imaginary part here. And once we take the complex conjugate of that, it's just with a plus. And minus X and plus X, you add them together by the property of exponentials. And then e to the 0 is 1. And so now we can apply the complex conjugate of this expression, and that will enable us to get rid of this I here. So you see this I has a plus in the normal C and a minus in the conjugate C. And now we have one thing to note here is that, remember, they had that, their beta had a 2. So this is really, 2 beta squared. And we don't have a 2. We just have gamma instead of 2 beta. So this is exactly the expression, which is it's kind of like the amplitude of our position, or in our case, our charge. Because when we take the real part of this complex solution that we assumed, we just have that A is the amplitude at which the position in this case, or the charge, goes up and down. And this phase is determined in a similar manner to just, the phase isn't too important for this lab, but this is, the easiest way to derive it. So let's see. I guess one other thing I can mention while I'm here, before I go to the chalkboard, is that we are not using our tried and true y equals mx plus b is nowhere to be seen today. So there are a variety of other fitting methods. So what we do when we take in y equals mx plus b, in our last few labs, was we're fitting our data to a linear equation. This, however, is not a linear equation. So what we're going to do is use, I've been researching this so-called orthogonal distance regression all day, and I still can't understand it. Neither could Rich. This was actually written by a TA last year. So I don't know exactly how it works. What I can tell you is how it works. Your x values for it. Again, x and y don't really make sense to me, with this equation here, but I'll explain how to use it at least. Your y's are your amplitudes. So for instance, a over here, or your v's, for instance, and the x's are omegas. So you use it in the sense you feed it kind of guesses. These are like what we'll end up doing. I'll show you over here in the lab rubric. What you end up doing is you find things theoretically. You think, oh, okay, this is what things should be, and then you feed the system. If any of you are computer science people, you probably, or maybe math people might know, what this regression technique is, which would be cool if you told other people. And you kind of feed it guess solutions, and then the code will run through and say, okay, here's my data. How do I fit it to something that should look like this? And one other thing to note, I'll just mention while I'm here. This, was my theoretical version, or my theoretical. Theoretically, that's what it should be. That's my gamma coefficient. It's like how fast my graph dies off. So here we had, this was the amount of time it took for it to decay. And now this is like how quickly it decays. It's like a measure of, if you can imagine, if this is time and we're taking 1 over time, it's kind of like a speed or a frequency or something. So it's kind of telling me how quickly my curve will die off. The fitting for this is not good. So because the code, it would be nice if they had the code, somewhere up here that you could look at, but they don't. So I don't know. This is kind of, a black box that you're putting things into. Oh, maybe I should have read this. Didn't read that. I'll read that. Yeah, so this is a awful fit. For instance, this was what theoretically it should be, and I, ended up getting like 30,000 versus 12,000. So, one thing I wrote on the chalkboard was just to take note of the differences. So for instance, comparing your first plots to your second plots and third plots, just take note of, is it bigger? Is it smaller? Because that will be, that will end up being sufficient for the lab. Mostly what you're doing is you're taking data, you're fitting it to this curve, and you're looking at different plots, and you're saying like what are the features that change as I change different parts of my circuit element and things like that. So I'll stop now, and let's see. Okay. And then I'll just go back to troubleshooting on the board. Let me stop the recording, and I'll, as usual, post this to the